Hello students, this is Professor Chalai, and in this video we're going to look at balancing ionic equations. By the end of this video, you should be able to write complete ionic equations, identify spectator ions, and write net ionic equations. As always, you can follow along with our Chapter 4 workbook. Now, before we get into what all those types of chemical equations are, let's look at a practice problem in balancing a chemical equation. Let's look at number 5. So number 5 gives us a chemical reaction with aqueous solutions of calcium chloride and silver nitrate, and they're mixed together producing aqueous calcium nitrate and solid silver chloride. So let's write this equation down and balance it like the question asks. So we have calcium chloride, so that's CaCl2, and it says that it's aqueous, so that's just AQ, plus AgNO3, that it also says is aqueous, so let's put that down. And it produces aqueous calcium nitrate, so that's CaNO3 2, aqueous, and solid silver chloride, so that's AgCl, solid. And let's balance this equation. We can use the guess and check method. So in this first one, we have two chlorines. We have one chlorine on the right hand side, so let's just make that whole thing a 2. That gives us 2 silver, so let's make this silver a 2. That gives us 2 nitrates. We have 2 nitrates over here, so that all looks balanced, but let's just double check. Calcium 1, Cl, 2 chloride ions, 2 chloride over here, 2 silver, 2 silver, 2 nitrates, 2 nitrates. Okay, so we're balanced. So this is a balanced molecular equation that we've looked at before, but we're dealing with ionic compounds here. We're dealing with salts that are soluble. In this case, it's calcium chloride and silver nitrate. Let's take a look at what happens when a salt dissolves. So let's look at a simpler salt, NaCl. We know that NaCl, table salt, can dissolve in water, and when it dissolves, it actually produces 2 ions, the separate ions that make up the salt. It produces Na plus ions and Cl minus ions. And then these ions are just floating around your solution, surrounded by lots and lots of water molecules. So any salt solution, whenever we see the symbol aqueous, what we should be imagining is that that salt is split apart into separate ions and floating around randomly in our solution. So in the example for this question, we have, let's say, AgNO3, silver nitrate. Same thing. We have Ag and our NO3 ions. When they dissolve in solution, right, they're aqueous. So when they dissolve in solution, what we should see floating around is Ag plus ions and NO3 minus ions. So in order to represent what's actually happening, we will write what we call a complete ionic equation, where we separate all of our ions out. So let's just write the definition for that first. So it's an equation where all dissolved ions are explicitly written. All that is to say is whenever you see an AQ symbol, you break it apart because in solution they exist as separate ions. So before I continue, let me just label. The first one would be labeled a molecular equation, which is what we've looked at in our previous video. This is our molecular equation. Let's look at the complete ionic equation now. So we have CaCl2, and CaCl2 breaks apart into Ca2 plus ions, aqueous, we almost must remember. The Cl2 gives us 2 Cl minus ions. Note that the charge is balanced, 2 plus charge and 1 minus charge, so that's all balanced. Let's look at the second compound, silver nitrate. We have 2 silver, so that's 2 silver. Silver has a charge of +1, so AQ. Plus 2 nitrates, so 2 NO3 minus AQ. two positive charges, two minus charges, so they balance out. And if you're not sure what the formula for these ions are or what their charges are, this is where our ion table comes in that we had to memorize. Okay. On the other hand, we have CaNO3 2 aqueous, so that breaks apart into Ca2 plus again, aqueous, plus 2 times the NO3 minus, aqueous. Again, we have two 1 minus charges and the 2 plus charge, so that balances out. And then finally, we have 2Ag plus aqueous plus 2Cl minus aqueous. So that the charges balance themselves. Sorry, we don't have any of that because this is a solid. It's not aqueous. So this remains the same. This remains 2AgCl solid. Only the aqueous ionic compounds get separated into their positive and negative charges, their positive and negative ions. So that's a complete ionic equation. So this gives us more of a complete picture of what's happening in our solution. We see that the calcium starts from Ca2 plus and it ends up at Ca2 plus. Nothing really happens. So let's just put a temporary stroke through that. We also see that the 2NO3 minus on the left-hand side is the same as the 2NO3 minus on the right-hand side. So because those ions did not change in the chemical reaction, we call those spectator ions. So spectator ions are ions that do not take part in a chemical reaction. In this case, they're usually here just to balance out the charges from the compounds that we had. So what that leads to is what we call a net ionic equation. So the one that we just wrote was a complete ionic equation with every ion broken apart. In our net ionic equation, we just include the ions that do take part, the compounds that do change in the reaction. So here we have the 2 chloride minus aqueous plus the 2 silver plus aqueous going to give us our 2 silver chloride solid. Those are the only things that change. And so that's our net ionic equation, or in other words, our net ionic equation is simply the equation showing only the changes that occur in an ionic equation reaction. So there we have it, the types of ionic equations. The regular equation, we just call that a molecular equation. Once we break everything that is aqueous apart, we call that a complete ionic equation. And once we cancel out all of the ions that remain the same on the left and right hand sides, we call that a net ionic equation. Let's try number 6. To see if you can figure it out for yourself, pause the video, try to work number 6 in writing the balanced molecular, complete ionic, and net ionic equations, and then I'll go it over with you. Okay, let's start with the molecular equation. Okay, so in here we have carbon dioxide. It doesn't say what state it is, we'll call it a gas. It's dissolved in aqueous sodium hydroxide, so that's sodium hydroxide, NaOH, aqueous, goes to give us aqueous sodium carbonate. Sodium has a charge of +1, carbonate has a charge of 2 minus, so we need 2 sodiums to balance that out, but that's aqueous, plus liquid water. So H2O, liquid. So that's our unbalanced equation. Let's try to balance this. Let's look at sodium. There is 1 sodium on the left, 2 on the right, so let's put a 2 there. That gives us 2 sodium. Let's counter our oxygens now. So we have 1 oxygen, 2 oxygens from the carbon dioxide, 2 oxygens from the water, 2 oxygens from the NaOH. We have 3 oxygens from the carbonate, and we have 1 oxygen from water. Oxygen is balanced. Let's look at hydrogen. We have 2 hydrogens on the left-hand side, we have 2 hydrogens on the right-hand side. That's balanced. So this is our balanced molecular equation. Let's look at our complete ionic equation. Remember, in our complete ionic equation, everything that is aqueous we break apart, everything that is not aqueous we keep together. So carbon dioxide gas is not aqueous, so we still keep that as carbon dioxide gas. Sodium hydroxide is aqueous, so let's break it apart. We have 2 sodium, so that's 2Na, it has a charge of +1, aqueous, plus 2OH. Hydroxide has a charge of -1. This is all found in your ion table that you had to memorize. So those charges are balanced as they should be. This all goes to give us, there's 2 sodium again here, 2 sodium plus 1 charge, aqueous, plus CO3 has a charge of 2-, it's a carbonate ion, aqueous. This is aqueous, that's why we broke it apart. And then we go to H2O liquid, that is not aqueous, so we just keep it together, H2O liquid. Alright, so that's our complete ionic equation. Let's look at our net ionic equation. Net ionic equation, we just ignore all of our spectator ions. So let's figure out which ones are spectator ions. Here we have 2 sodium on the left, 2 sodium on the right. That remains the same, so they're spectators, they don't do anything. Everything else changes form some way or the other. Carbon dioxide gas goes to form carbonate aqueous. 2OH- helps to form the water. So everything else constitutes the net ionic equation. So we have carbon dioxide gas plus 2OH- aqueous goes to give us CO3 2- aqueous plus H2O liquid. As always, you would want to make sure that your atoms and charges are both balanced. So we have 1 carbon, 1 carbon, 2 plus 2, 4 oxygens, 3 plus 1, 4 oxygens, 2 hydrogens, 2 hydrogens. So the atoms are balanced. Like, let's look at the charges. We have 2 times -1, so that's 2- charges, and we have a 2- charge there, so the charges are also balanced. So then our equations are all balanced. Try number 7 on your own. Write the molecular, the complete ionic, and the net ionic equation for this reaction that we give you in number 7. Pause the video, try it for yourself again, and then come back and we'll do it together. Okay, let's start with the balanced molecular equation. We have NaCl plus H2O goes to give us NaOH, H2, and Cl2. Alright, so let me just write that down first. NaCl aqueous plus H2O liquid goes to give us NaOH aqueous plus H2 gas plus Cl2 gas. Now I look over here where there's 1 Na, 1 Na, so that's balanced. Let's look at Cl. 1 Cl on the left, 2 Cl's on the right, so let's make this whole thing a 2, but then that gives us 2 Na, so let's go back over here and make that Na a 2. Alright, so we have 2 Nas, 2 Nas, 2 Cl's, 2 Cl's. We have 2 H's on the left and 4 H's on the right, so we need to make that a 2. Yeah, so 2 times 2 is 4. We have 2 times 2 H's here, 2 H's in the hydrogen, that's 4. Alright, now let's look at oxygen. We have 2 oxygens on the left, 2 oxygens on the right, so that's all balanced. So now our equation, our molecular equation is balanced. Let's delete some of these extra marks that I've added. Alright, let's look at the complete ionic equation now. I like to label them so that I don't know which equation is being written. Everything that's aqueous gets broken apart in the complete ionic equation. So we have 2 NaCl. Na breaks apart into Na+, and there's 2 of them, plus Cl-, there's 2 of them, aqueous. Always make sure you write your state symbols, your aqueous, your charges, everything must be consistent. Alright, 2H2O liquid, that doesn't break apart, so it remains 2H2O liquid. Goes to give us 2 NaOH aqueous, so that breaks apart into 2 Na plus aqueous plus 2 OH minus aqueous. And then H2 gas is a gas, so it stays the same, and Cl2 is a gas, so it stays the same. Okay, let's look at our net ionic equation. Before we write that, let's look at our spectator ions. So 2Na on the left, 2Na on the right, that stays the same. Cl minus on the left, but Cl gas on the right, so that changes. Water on the left, and then various things on the right, so that also changes. So what we're left with is 2Cl minus aqueous plus 2H2O liquid, going to give us 2OH minus aqueous plus H2 gas plus Cl2 gas. Now, if we haven't skipped any step, the net ionics should also be balanced in both atoms and charges, but because I like to verify, let's do so. 2 chlorine atoms, 4 hydrogen atoms, 2 hydrogen plus 2 hydrogens, 4 hydrogen, and then 2 oxygen on the left and 2 oxygen on the right. So the atoms are balanced. What about the charge? We have 2 times a 1 minus charge on the left and a 2 times a 1 minus charge on the right, so the charges are also balanced. So I hope you got these for the net ionic and complete ionic equations. If you're still struggling with them, let me know. But try number 8 on your own. And as always, when you unpause the video, we'll go over them again. Okay, number 8, let's work on the molecular equation first. So what do we have? We have the reaction between aqueous sodium sulfate. So sodium has a charge of +1. So let me just write it over up here. Sodium has a charge of +1. Sulfate, it has a formula of SO4 2-. So to make this work, we need to multiply this whole thing by 2 and multiply this thing by 1. So our formula ends up being Na2SO4. And the equation says that it's aqueous. We add that to, let's look at the second one, aqueous ammonium phosphate. From our ion table, we'll see that ammonium has a formula NH4 with a +1 charge, and phosphate we'll see has a formula of PO4 3-. So to make this all balanced with charge, we need to multiply this guy by 3 to make sure it's 3 positive charges. So the compound for ammonium phosphate will be NH4 3 PO4 aqueous. Do you see how that works? Okay. Let's see what it forms. It forms aqueous sodium phosphate. So sodium has a charge of +1, phosphate has a charge of 3-. So to make this work, it will be sodium times 3 phosphate. And they told us it's aqueous. And then finally, aqueous ammonium sulfate. Ammonium has a charge of +1, sulfate has a charge of -2. So we need 2 ammoniums to make the charges balance. So it's NH4 2 to SO4 aqueous. Okay, so that's our molecular equation. Now let's balance it. This one might seem tricky at first, but let's look at it. We see that there are 2 sodiums on the left and 3 on the right. Now what factor can we use for sodium that makes it such that they're equal on both the left and the right? Well, if we multiply the ones on the left by 3 and the ones on the right by 2, we realize that we'll get 6 sodiums on the left and 6 sodiums on the right. Again, this is a guess and check method. If you use the longer method, you'll also come to the same result. I'm just showing you some quick ways to figure this out. So now that we have 6 sodiums on the left, 6 sodiums on the right, that seems okay. But what about everything else? We have 3 sulfates on the left. On the right, we only have 1 sulfate. So let's make that a 3. We make that a 3 sulfate. That gives us 3 ammonium. So, and on the left-hand side, we have 3 ammonium. So it's balanced. Okay, let's see what else we have. Phosphate on the left. Sorry, we have 6 ammonium on the right-hand side, but only 3 on the left. So let's make this a 2, and that gives us 6 ammonium. So 6 ammonium on the left, 3 times 2, 6 ammoniums on the right, so that's balanced. Okay, now let's see what else we have. We have 2 times phosphate, we have on the left, 2 times phosphate on the right, so that's balanced. So now everything should be balanced just by adding those numbers. If you want to see how I did that again, you can rewind the video, but it's basically starting by just finding a factor that I could multiply the sodiums on the left and the right with that make it so that they have equal numbers. In this case, I chose to multiply it by 3 on the left, 2 on the right, and that just comes with some experience. You can use the long method and you'll be able to figure out the same thing, just taking a longer time. Okay, let's look at the complete ionic equation. Again, what this means is that every single aqueous ion, we break apart into separate, every aqueous compound, we break apart into separate ions. So let's see what we have. We have 3 sodium sulfate, that's aqueous, so we have to break it apart. So 3 times 2, that gives us 6 sodium plus, it's aqueous, and 3 SO4, 2 minus, right? That's the charge, aqueous. Okay, what else do we have? This is also aqueous. It's ammonium phosphate, and there's 2 times 3, so there's 6 ammonium. So we do 6 NH4 plus, that's the formula for ammonium. And we have 2 phosphate ions, to 2PO4, 3 minus, aqueous. And by the way, each of these cases, the charges are balanced. We have 6 plus 1 charges and 3 2 minus charges, so that's balanced. And for the ammonium phosphate, we have 6 plus 1 charges and 2 3 minus charges, so those are balanced. All right, for the product side, we have 2 times 3, that's 6 sodiums, aqueous, plus 2 phosphates, so that's 2PO4, 3 minus, aqueous. And then finally, we have, this is also aqueous, so we need to break that apart. We have 3 times 2, that gives us 6 ammoniums. Recognize that I'm writing the prefactor, the correct formula for the ion, the correct charge, and the symbol all need to be included for these equations to be completely correct. And we have 3 sulfates, so 3 SO4, 2 minus, aqueous. All right, let's look at the net ionic equation. So now, before we can do that, let's figure out the spectator ions, the ions that do not change. So on the left-hand side, we have 6 sodiums. On the right-hand side, we have 6, so that cancels out. On the left-hand side, we have 3 sulfates. On the right-hand side, we have 3 sulfates, so that cancels. On the left, we have 6 ammonium. On the right, we have 6 ammonium, so that cancels. And on the left, we have 2 phosphates. And on the right, we have 2 phosphates, so that cancels. Well, look at that. Everything cancels out, because everything were aqueous. So we do not have a net ionic equation. So in these cases, you should strongly write no reaction, because the ions stay the same from the beginning to the end. Nothing really changed. The ions are just there floating around. No reaction actually happens. All right, that will bring us to the end of writing ionic equations. Just a reminder that there are three types of equations that you need to consider when you're doing these. The full molecular equation that has all of the compounds still together. The complete ionic equation that breaks apart everything that's aqueous. And the net ionic equation that includes only the things that change in equation. Any spectator ions are ignored. In some cases, you'll find that all of the ions are spectator ions, in which case you should write no reaction for the net ionic equation, because in those systems, no reaction actually happened. All right, this brings us to the end of this video. In the next video, we're going to talk about different types and classes of reaction, and I'll see you then. Bye.